Alright, afternoon. My name is Nolan,
I'm Wallace. I'm Weston.
and we're here today to discuss friction welding. So we're going to do this through 5 stages. First, we're going to give you a brief background and the introduction. Then we're going to go into the process description and methodology. Then we'll move into advantages and disadvantages, followed up by innovations and advancements of recent. And then finally, we'll give you some insights and reflections we have while studying friction welding. Alright, introduction. So friction welding is a solid state joining process which uses heat generated by friction between moving workpieces. It has no filler materials, fluxes, or shielding gases, making it an environmentally friendly process, and it produces strong defect-free bonds. So under this broad realm of friction welding, there's 3 different types. The first one being rotary friction welding, where you have a piece that's not moving and then you have a rotating piece. Go together like that. Then there's linear friction welding, where you have 2 pieces going like this together. And then finally you have friction stir welding, where there's a flat piece and then a tool goes on top of that. So we've got a video here next of rotary friction welding, which is sort of the main one. So yeah, there's the rotating piece, the other one's not moving. And eventually, produce enough heat, metal starts to soften, they'll be forged together. Alright, and then why choose friction welding? A great advantage of it is that you can join dissimilar materials very easily. It creates superior joint properties such as high tensile strength, excellent fatigue resistance, and minimal porosity, cracking, and distortion. As mentioned earlier, there's no filler materials, which leads to lower material cost and minimal waste. And finally, it's a rapid process, which leads to increased efficiency.
Now I'm going to talk about the process description and methodology. So first off, the raw materials and our initial inputs. The raw materials include things such as metals, alloys, and some composites, as mentioned before. Friction welding allows these raw materials to be joined. The surfaces of the materials must be clean and flat to ensure proper heat generation during the process. Contaminants such as oil, rust, or coatings can negatively affect the weld quality. And the initial inputs are the work pieces, which are typically cylindrical or flat. Precise machining and preheating or post-weld treatment may be applied for optimal properties. The friction welding equipment is these machines provide rotational or linear motion, clamping systems, and hydraulic pneumatic systems applying forging pressure. Rotary machines including a spindle which rotates a workpiece and a stationary chuck which holds a opposing piece. Advanced machines offer computer-controlled monitoring as well. And then for friction stir welding, you need a non-consumable tool such as hardened steel or tungsten carbide. Pin and shoulder geometry critical for weld quality, and fixtures and clamps to stabilize the workpiece being worked on. So the first stage is the friction stage. Workpieces are pressed together, relative motion generates frictional heat, and the material is plasticized without melting. Then comes the forging stage, where motion stops and axial force is applied. The plasticized materials then flows and bond metallurgically. And then lastly, the cooling stage, where the weld solidifies under pressure. Fine-grained microstructure is formed, improving the strength and toughness. And the key advantage of this is there's no melting, minimal defects like porosity, cracking, and it's ideal for high-stress applications. And the output in the final product is the high-strength, defect-free welds with fine-grained microstructure, which enhances the tensile strength and fatigue resistance. There's no fusion zone works to eliminate segregation, solidification, cracking, and high dimensional accuracy and excellent surface finish with very little post-weld machining needed. Some of the real-world applications can be used in aerospace, automotive industry, and energy industries as well. where these high performance joints are critical. Some of the advantages and disadvantages now. The superior weld quality that proves stronger joints than traditional methods, sometimes even surpassing electron beam welding for similar materials. And they're also, again, capable of joining dissimilar materials. They're very energy and cost efficient, lower power consumption compared to electric arc or flash bolt welding, and cost saving by minimizing expensive material use in non-critical areas. And it's very automation friendly, with precise control over rotational speed, axial force, and welding time, making friction welding highly suitable for mass production in automotive and aerospace industries. Some of the limitations, however, are just some geometric restrictions, primarily limited to circular or rotationally symmetric components due to the motion requirements, making friction welding not suitable for irregular or complex geometries. There's some specialized equipment needed. You need friction welding machines, making it not ideal for on-site or field welding. And then very niche application focus. It's best suited for specific areas like a drive shafts or aerospace components. Friction welding is not very broadly placed in fusion welding methods like GMAW or TIF.
So then I'm going to talk about some innovations and technological advancements. So linear friction welding has gained traction in the aerospace industry, mainly in the use of the engines department. They're making the turbine or the rotor that spins inside the engine chamber. So as said earlier, there's been improved energy efficiency, shorter cycle times, and greater precision in the field of frictional welding. And then there could be a future expansion within the automotive industry and could replace some fusion welding processes, and the lower production costs will streamline manufacturing. And then the airframe manufacturers encourage supplier investment in the modern linear frictional welding equipment. So in relationship with materials and techniques, non-fusion frictional welding enables joining dissimilar materials, as said earlier. It's one of the big, the high advantages of friction welding. Lower temperature techniques are also being explored, just because sometimes there can be overheating within the equipment. Frictional stir welding includes benefits such as being ideal for polymers, improves high weld quality, higher weld quality than other than lasers and ultrasonic welding. And then microstructures, altercations, and tool geometry optimization further improve joint strength and durability. So again, going back in on that durability aspect of it. And then successful joining of copper and aluminum despite different metal melting points. So again, back on the aspect of different materials can be frictional weld together. So the implications of the process is there's high friction and forging forces essential for effective linear frictional welding. So temperatures can be high around the machine. Then joining dissimilar materials through non-fusion welding improves strength and reduces defects. And then frictional stir welding specifically eliminates common solidification defects and yields more durable and uniform welds. And then continued process and material improvements drive an adaptation across aerospace, automotive, and polymer industries. So some insights and reflections. So some key takeaways here are that automation significantly enhances frictional welding efficiency. So with the introduction of AI and different automation, it can improve just overall frictional welding. The precise control over rotational speed, axial forces, and welding time makes frictional welding ideal for automation. And then automation in aerospace industries increasingly adapt automated frictional welding for higher production efficiency and consistent weld quality. That's a big takeaway, is it's usually way more consistent than if someone's doing it by hand every time. Robotics and advanced control systems further boost manufacturing productivity also. And then frictional welding reduces material waste and supports sustainability efforts. There's no need for filler materials, again, as talked about previously and throughout the presentation. And then there's minimal waste, again, that's another, opposed to normal welding whenever someone's there with the welder in their hand. Lower energy consumption opposed to again, manual welding, and then there's sustainability that goes along with all these other ideas. That's all.
It seems like it's quite a niche area. So what's going on with this industry? Are there companies just to do the friction welding, or are they just a part of a small branch in a big factory?
I would assume it's more for like Boeing, Delta, all those things that make large, like manufactured airplanes, I'm assuming, is what they use it mostly for, because it's very hard for a common company or a smaller company to get friction welding on site. And it's very niche as well. It's mostly like for circular drive shaft components, so automotive and aerospace is, for right now, most of where it's happening.
Yeah, the Boeing was a big one that I saw whenever I was doing the research about it going into like aerospace industries. And the big reason is just getting it in the door is very expensive, but once you get it in the door, the production cost is very low, so it's just, you gotta initially put a big investment up front.
Okay. So now if we go to materials, metal to metal, I think that I suppose are there any limitation on what metal can what type of metal can be friction welded or not, and can we use metal and polymer and things, different types of materials?
I would assume there is, or I guess.
I know you can for sure do like metals and alloys together. Saw that a lot in my research. I never really saw anything about metal to polymer, but I'm sure that's something they're working on within this field probably.
Yeah, the big thing was just like it has to be a smooth material. It can't have like rough finishes or anything. But I don't know about the polymer to metal, but I know for metal to metal or metal to axon, just if the materials are smooth, I think that it can have friction. It can actually frictional weld together.
Okay. Good. Any other questions?
Yeah, so for the friction welding, actually, so it's a high level thing if you're talking about like friction steel welding. For like rotary friction welding, actually it's not that